conservation of momentum. Go ahead and cut off the border and cut out every piece of paper. Momentum is conserved in a closed system. So first of all, just make sure we don't forget, momentum is mass times velocity. Okay? Conserved. What does it mean to conserve something? Okay? Conserved means it's saved, it's kept, it's preserved, it is not lost. Okay? So, conservation of momentum means the momentum is not lost, and it says in a closed system. So we've talked about systems before, okay? A closed system, this means there are no external forces. If I could spell right. No external forces. Simply put, no friction. No friction, no motors, nothing else adding to the system. Okay? So, momentum is conserved. Now, of course, that whole no friction thing, kind of impossible. It's just theoretical sort of thing. But, hey, we go with it. Because it makes the math doable, and it helps explain why things move the way they do. So that conservation momentum we're specifically talking about when we are dealing with collisions. So, the total amount of momentum in a system does not change even when objects collide. What does it mean by collide? Right. That's the fancy science word for crash. Chocar. Okay? So, trying to get two objects to crash into each other. Right? When they crash into each other, the momentum isn't lost. All right? It might transfer back and forth between the two objects, but it's not lost. Going to draw a little cart, label it 1. Draw another little cart, label it 2. They're going to move towards one another so that they collide. Now, when they collide in a situation where there is no friction, if they were to get all bent up and everything like cars do, there's friction involved. If there is no friction, the object itself will not be affected, and there's one of two options. Either the two objects will stick together or they will bounce off each other. Okay? So, if they bounce off each other, we call it an elastic collision. If they stick together, we call it an inelastic collision. These are the two possible outcomes. All right? Elastic collision or inelastic collision. So that means that we're going to draw our little carts again. Bounce off each other. So we'll say cart 1 will now move to the left. Cart 2 will now move to the right. Inelastic collision, they'll stick together. So cart 1 and cart 2 are now stuck together and they will move together. Okay? So objects stick together and become one object and move together. Conservation momentum means that the net momentum before the collision is equal to the net momentum after the collision. Now we've talked about net force before. Net momentum. Momentum, lowercase p, net momentum is equal to the net momentum after. So the net momentum before and the net momentum after, it's the same number. That stays the same. So when we're talking about mechanical energy, it stays the same. Doesn't matter where you are. This is net momentum stays the same. It doesn't matter how they collide. We're going to go through an example here. Cart 1 and cart 2. Okay? Cart 1, we're going to say 50 kilogram mass. Cart 2, we're going to give it 100 kilogram mass. Cart 1, 4 meters per second. Cart 2, we're going to give it the same, 4 meters per second. Now, little detail here. Remember when we talked about velocity, and I said velocity is a vector measurement? It has direction. So, when I show you this, 4 meters per second to the left, to the right, and 4 meters per second to the left, what does that mean? The one moving to the right is positive. The one moving to the left is negative. This is crucial, vitally important that you remember this and you recognize this. If it's moving to the left, that's a negative velocity. If you ignore that, then the whole conservation momentum thing doesn't work. Okay? So you have to pay very close attention to what direction the objects are moving. Negative is to the left, positive to the right. Okay, so we have these two cards before they crash. They are our system. What is the momentum of car 1 before they crash into each other? Mass times velocity, right? 50 times 4, 200. The momentum of car 2 before they crash. Mass times velocity, negative 400. All right? Kilogram meters per second, including our units there. So the momentum of car 1 before, 200, car 2 before, negative 400. What is the net momentum of our system? Add those together, you get a negative 200. That negative 200 does not change. The net momentum does not change. We're going to make this an inelastic collision. They're going to crash into each other and stick. Car 1 and car 2 have now become a train. Okay? When they collide, is that going to cause the individual mass of those two to change? No. But now, because it is an inelastic collision, they have become one object. So what is the mass of my one object? 150 kilograms. Does that make sense so far?
Yes.
All right. Now, we're talking about three basic variables: mass, velocity, and momentum. We know the mass is 150 because now they've combined. What else do we know?
Net force.
The net momentum does not change. Now that they're moving together, they have the net momentum is still negative 200 kilogram meters per second. What do we not know? The velocity. So, momentum is mass times velocity. Put in the triangle. Velocity is momentum divided by mass. We have the momentum of the train. We have the mass of the train. We will find the velocity of the train. So I take that negative 200. That's the momentum, divided by the mass of 150. calculator. Negative 1.3. All right, so what does that mean, a negative 1.3? Okay, we're talking about velocity. So like initially, velocity of 4 and negative 4. Okay, so 1.3 is definitely less than 4. It's negative, so what direction is it going? It's going to the left. Draw a little arrow because it's only 1.3 compared to 4. Negative 1.3 meters per second. The most difficult part with these is keeping track of the information. We have a mass of object 1, we've got a mass of object 2, we have the velocity of object 1 before they crashed, and the velocity of object 2 before they crashed, and then we have a velocity after they crashed, and then the mass of them combined. So there's a lot of different, so right here we have 3 different masses, 50, 100, and 150. We've got 3 different velocities, positive 4, negative 1.3. All right? So there's a lot of numbers to deal with. It's keeping track of the numbers and paying attention to how you're moving the information around so you don't get lost. So you have to be careful with the numbers. The easiest thing to do is make sure you label everything. The initial momentum, you might want to label it that way. The mass of object 1, the velocity of object 1 initially, a little I there. The mass of object 2, the mass of object 2 initially. Sorry, velocity. So the initial velocity, the mass isn't going to change of object 2, but its initial velocity is going to be different than its final velocity. Its velocity will change. Okay? So I would label this final mass because this is an inelastic collision. They combined masses. And this is a final velocity. Okay? Notice we have momentum of separate objects, but then we have net momentum. The net momentum doesn't change. Okay? It's still negative 200. Before and after the crash and any point in between, that momentum is still negative 200. The net momentum. Okay? So there's a lot of numbers here. You got to be able to keep track of labeling them all so you don't get lost. Now, you have 2 more pieces of paper left. We're going to put these on the oops page. I want you to write on the first line, elastic collision. And then halfway down the page, I want you to write inelastic collision. Okay? There's formulas for these. Now the formula, if you're really good at algebra, totally makes sense. If you suck at algebra, it's going to be like, what is that? So, you can use the formulas if they're helpful. If they're confusing, you don't have to use them. All right. So here's the 2 formulas. Those of you who are good at algebra, can you guess which one is which? Notice they start off exactly the same. Mass of object 1 multiplied by the mass of the initial velocity of object 1. The mass of object 2 multiplied by the initial velocity of object 2. So they start off the same. And then this is supposed to be the before the collision, and this side's after the collision.
The first one?
Is this going to be elastic or inelastic? So the masses, here we're adding them together. So that means the 2 objects stuck together. What kind of a collision is it stuck together? Inelastic. Elastic means they bounce off. Let's draw this. Elastic collision. First, they are traveling towards each other, and then they'll bounce off. So the before, and then the after. This is a classic example of an elastic collision. Once they've collided, they bounce off and go opposite directions. Inelastic collision starts off similar, moving towards each other, but this time when they collide, they become one object, and they will move together. If you like color coding, you need 6 colors. Okay, so the mass of object 1 doesn't change. Okay? The mass of object 2 doesn't change. However, the velocity of object 1 before the crash and the velocity of object 2 before the crash will change. The velocity 1 before the crash will be different from the velocity 1 after the crash. And the velocity, it's the only color I've got, after the crash for object 2 is different than the initial and final are different. Okay? So, that kind of helps understand where those numbers are coming from. Okay? Does that make sense?
Yes.
Similar, we can color coordinate inelastic collision. So again, the mass of object 1 is added to the mass of object 2 after they've collided. The mass of object 2, we add those two masses together because now it's one object as a train. And that initial velocity for object 1 and the initial velocity of object 2 becomes one final velocity together because they're acting as one object. Okay? Does that make sense? So if you're good at algebra, you can just plug all the numbers into a formula and go with it. The way these problems are always set up is that you're given all of the information but one. So you're given like everything but the initial velocity of object 1, or everything but the final velocity. Okay? You're given all the information, you have to piece it all together and find the missing piece of information.